Okay, if not, I will move on to the second question. The second question is called strange functions. Basically, you have designed a function that has two operations. So branch one is if x, x is your input number. And according to the problem statement, I think x is really large. X is to, let me see, 10 to the 2 to the power of 10 to the power of 5. Something that is really big. We can barely represent it by long. So that it offers that we should mock the number. Let me check again. Yeah. It's 10 to the x is 10 to the power of 2 times 10 to the power of 5. So it's a really large number, and it's hard to imagine. So basically, this number tells us you should not brute force to simulate. This is telling you do not simulate because the simulation takes forever. The size of the x already discourages you from attempting it. Um, it says the x you will be given like a random number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, a random number. So we would observe this number. If x has any digit outside of binary 0 and 1, if this you will replace each digit from the odd number. You will set it to 1 if it's odd. You will set it to 0 if this number is even, and then return the result. So basically, you update the x accordingly. Otherwise, if the x is already a binary number, you will just do -1 to x. Since x is really large, um, we should replace every answer here, the application to mod this 10 to the power of 9 plus 7. So in my observation, I find for any number in the case one, it will transform the number into a binary number. So doesn't matter what x was originally, depending on if it's even or not, you will replace the number into 1 and 0. So basically, it will make it into a binary number. Now, once this number has become a binary number, there are two cases. If it's actually ending with 1, you will do -1. So you will see this arrow I draw. If this number is a binary number, if it's 1, you -1, it becomes a binary number ending with 0. And now this is a binary number ending with 0. You should further do -1 to it. So the last number, doesn't matter what the previous number is, the last digit actually become 9. This 9, again, let's go back to branch 1. There is a digit that is outside of 0 and 1. Now this is surely an odd number, so you will make this into a 1 again. And now this 1 will do x minus 1 again, and it goes to the cycle of 0. So I noticed there is an infinite cycle in case 2, and I know it's a binary number anyway. So I want to try to see what pattern I can find in transforming some binary numbers into 0 as it's required. So I represented out some binary number. Here are some binary number I tried. I go from the smallest binary number, which is 0, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So on the left-hand side is their binary representation. In the middle is the actual number. And finally, it's the actual steps I have tried out to make it into a 0. So for this 0, it's already 0, so there's 0 step needed to make them into 0. Now for the binary number 0 and 1, and all I do is just -1. Go into branches 2, and that made, so the binary number, if it's 0 and 1, then I applied branch 2 to make it 0, 0. And I know I have taken one step. And now for the binary number 1, 0, the numerical value represented is 2. Now it follows into branch 2, I do -1. So this 1, 0 actually become 9. And now since this is an odd number, I replace this digit with 1. And now this 1, it's follows in the branch 2. I do -1, it becomes 0 again. So I notice it's 3 steps. So, and I follow this pattern. Now I go to 1, 1. So for this binary 1, 1, it's an odd number. So I go ahead and replace the digit with like it's binary and it's odd. So I do -1. It becomes 1, 0. Surely I notice, oh, I have done operation for 1, 0 before. And 1, 0 takes 3 steps to become 0. And it takes me only 1 additional steps to go from 11 to 10. So I know the total steps is 4 without any doing this like the actual computation. I realize this 10 actually I pre-computed it, or depending on the previous answer here, I can use this answer directly. And I notice this pattern again at the binary number 1, 0, 0. So for 1, 0, 0, I used x minus 1, it becomes 99. And I applied this branch 1 again, it becomes 11. And then I noticed, oh, this 11 has been calculated before. I can rely on the previous steps 4 and add to it, 2 to it, and to get 6. And then I realized this pattern again and again. As you see, this 100, I can easily turn 101 into a 100, and this 100 is pre-calculated before. So I have noticed there is a dependency going on. It's like a recursion. Um, I surely noticed if the binary number it's like if the binary number numerical value it's odd, then the steps is just +1. I noticed if the binary representation numerical value is even, then it's just +2 from the previous steps. So we can actually confirm it. This is 3, so you know there is a +1. 3 plus 1 to get 4. Now this 4 is even, it's +2. 4 plus 2 is 6. So I can follow this pattern easily to generate all the steps needed for any binary numbers. So from this pattern, I can surely conclude, wait. So from this pattern, I can safely tell myself all number that is in binary form, I can find the operations needed. Now the problem can be condensed easily. So if I'm solving this on paper, I would say first reading x and then set the count to be 0. I've done nothing. Now if any of the digit x is not in, so if x not binary, you will use the branch 1 to make it into binary. So count plus plus and make it into binary. And now, since x is in on the 0 and 1 digit form, x is now binary. There is going to be some special cases where you are really lucky after in branch 1, the x already turns into a bunch of 0. So you should check for these special cases. When x is already 0, then the steps is just 1. Otherwise, if this x in binary form is not 0, you will transform the binary number into a numerical value. Because even though, well, you can use recursion, basically, f0 is equal to 1, f1, f0, which is numerical value 0, it takes 0 steps. f1, it's odd, it takes 1 steps. And then you can basically say fi, if I is even, then is fi minus 1 plus 2. If I is odd, then you can do fi minus 1 plus 1. However, if you know recursion, this is still an oven. solution. And x here is really big. X here is 10 to the 10 to the power 5. So it's quite impossible for us to actually go over this binary search and sorry, over this binary numbers and digit to actually rely on x numerical value. But we're actually not using x numerical value. We're using x digits representing the binary number. So how many digits can this x have is log 2 to the maximum of x can be is maximum 2 to the 10 to the power 15. This is handleable. So we can actually compute step-by-step processing this number in binary number digit by digit and get the answer. So let's interpret. So transform the number. Uh, so we can actually, so the idea of transforming the binary number back into numerical value is not actually feasible. So we should be interpreting the digital string as a binary number B. And then if we actually observe this pattern, you will find if this is a numerical value B, then the steps can be represented by 3 times B, 4 divided by 2. And then you take a floor into that. So there is a O1 solution to find exactly how many transformations are needed, depending on like what's the numerical value for B. So for step 5, so we can greatly compute 3b 4 divided by 2 and mod, since the steps should be mod by 10 to the power 9 plus 7, and then add to the step. Using this result, we add to the count and output the result. There is one thing I want to talk about in the implementation. So basically here you want this 3b 4 divided by 2 to mod this 10i plus 7. This b, the binary representation's actual numerical value is going to be very large. So no container is going to safely hold 3 times b. So here is my in my code I did so this is my mod value. So 10 to the power of 9 plus 7. This is exactly what I did in my code. This is a pseudocode I'm going to go over. So this is the steps. I actually avoid calculating the speed. This is a classic measurement for transforming a binary number, binary representation, back to the numerical value, but bound the numerical value within the 0 to mod, within the basically the mod limit. I'm going to explain shortly how you avoid kind of generating a really large number along the way. So here you reading this x as a string, that is our initial data, and you go into branch 1. You check for if any of the digits not 0 and 1. So the initial count is 0. So if the number is already binary, then you go into the step B directly. However, if the number is not binary, so you need actually phrase 1 to transform into binary. So the count is initiated to be 0, and then you basically change the number into binary according to its rule of whether it's odd or even. Now my step B is the special cases when after one step of transforming it into binary number, this number already becomes 0. So you should be removing the leading 0 from x because they contribute nothing. And then if this x, after removing the leading zeros, it's already 0, then that means using one step, we already make it into a 0. now it's in step C, so that's what we conclude. 3b 4 by 2 is actually the number of operation needed. However, b itself is really large, so we need to construct the binary number from the last digit back to the original number, but we need to constrain it within b mod is 10 to the power of 9. Basically, it's b mod mod, so mod here is defined. If you remember how we transform the binary number back to the original number is we always go from the last digit. And so for example, 111, we go from the last digit. The last digit is 1. 1 times 2 plus 1. Then this is 3. Basically, 1 is representing 3. And then to represent 111, you time this again, 2 times 3 plus 1. So it's 7. So you always do this b mod times 2 plus whether or not the last digit you are actually inputting is 1 or not. And then to make this big, really, really large b into the boundary where the question asks for within this mod bound, every time you do times 2 and then plus the last digit, you should always mod them by the mod. So you always get the last digit, and then starting from the last digit, you rebuild this b, and then every time to avoid overflowing beyond the mod, you mod. And now finally is once you compute this b within this mod sign, you use the 3b divided by 2. All this is just following mathematical transformation for the mod calculation. And this is how I solve this problem. Any question here?